Because I know a few people who've started companies that evolved into large search engines, I can share with you a few of their random notes from indexing the real world, that is to say, indexing the web in the real world. First thing to note is that the dictionary of terms in the web is not like the English dictionary. It's gigantic. It includes everything you could possibly think of. For example, all the numerals you can imagine, 1, 2, 3, and so on, occur on web pages and are interesting for people to search on. For example, searching for a serial number for your favorite or a model number for your favorite product is a numeral search, and we want to index on all those distinct numerals. Codes like words in programs are also things that people search on. You may have searched on them yourself in doing some of the homeworks for this class, right? And so commands in Unix or even variable names in programs are things that need to be indexed in the web corpus. Misspellings are often interesting and worthwhile to index. You could fix misspellings before you index things, but sometimes it's useful to index the misspellings because people may want to search for them. And of course, there's more than one language on the web. It's an international corpus of documents, and so we have all kinds of languages, including in multiple alphabets. Okay, and so this dictionary is just enormous. It goes on and on. As I mentioned earlier, another real problem in the real world is web spam. And people try to get their documents top rated. That's called search engine optimization. You can imagine how you could spam TF-IDF if you think about it. So in the old days of the web, early on, I remember people used to do the following. If you wanted to make Stanford look bad, you could put a document on the web that said Stanford, 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 lost the big game, right? And because this has such a high term frequency of the term Stanford, you might think it would get ranked highly in a TF-IDF ranking of queries for Stanford. So maybe this would be the number one document if you did a search for Stanford. And if you do this in a white text on the white background of a web page, you could put the word Stanford a bazillion times on that page and not even bother your human readers looking at that page. So in the bad old days of the web, when things were very primitive, this is how people would do spamming of techniques like TF-IDF. Obviously, people got a little smarter about this over time and started filtering out those sorts of hacks. But now you can imagine spamming PageRank. How would you do this? You want to create a bunch of links of documents to other documents that make those documents appear important. So you can imagine how you would generate a web server that would dynamically create documents that point to each other to create high page rank. And then you have to think about how a search engine might avoid such nests of interconnected dynamic pages intelligently. And this is a tricky topic that the search engines won't tell you everything about, but you can read about it online. Some real-world stuff actually makes life easier rather than harder. For example, as we said, terms and queries are Zipfian. One of the key things with that is that caches work very effectively. Because Justin and Bieber are such common terms in both documents and queries, we can keep them cached in memory very naturally, and we can answer queries for Justin Bieber out of cache without going to disk. And so the Zipfian quality of queries and documents actually means that the hot queries and the hot terms stay hot for a decent period of time, and we can use caching effectively. Another thing that comes up on the web is that queries are generally generated by humans, and they're very small, 1 or 2 words. This helps with both the work involved in answering queries and in the techniques we use to achieve good precision and recall. Another issue that's really nice for bulk loading of indexes is that users don't notice minor inconsistencies in answers. A user may not notice if a small fraction of the web is missing from your search index when they do a search. They might just reissue their query if they're confused and get back a better answer later. And so it's possible, for example, when you're updating indexes to take a little bit of the web offline in your parallel web search engine and not have users even notice. Finally, one of the challenges that was faced by search engines early on was the challenge of running enormous internet services at scale with 24/7 availability for billions of users around the world. Search engines essentially were among the first systems ever built for this kind of service level. And search engines were actually nice in this domain exactly for the reasons that we see above. Users don't mind minor inconsistencies in answers. Queries are Zipfian, so most of the work is hot query work, etc. These techniques allowed the search engines to grow without being perfect, and it allowed them to handle large fractions of their workloads out of memory. Okay, and so as search engines developed tricks to scale and grow, some of the keys were based on the domain of search engines, which is a little bit different from the domain of relational databases and transactional queries. And so the loosey-goosey nature of search has actually been key to its ability to scale and to the growth of the internet in general. Lots of interesting lessons there around sacrificing exact query answers for achieving scale and availability. And this is a long topic that's probably better suited to another class on massively scalable systems. But we have a flavor of it here from our notion of parallel query processing and some of these ideas of the loose precision and recall metrics around information retrieval that we've learned in this lecture.